I am Domenico De Sarno, a PhD student at University of Naples Federico II. I've spent almost 3 months in Recife at Universidade Federal de Pernambuco under the supervision of Professor Leonardo Guimares. There I learned to use the software CodeBright that allows to perform thermohydromechanical analysis. The activities I worked on at Universidade Federal de Pernambuco were about the modeling of an experimental test that was performed on a dam on the Po River embankment some years ago. The results of this research are published on the paper Research Study of the Hydraulic Behavior of the Po River Embankments by Calabrese et al. 2013. The site is in Viadana, a city in the north of Italy. In the picture, the stratigraphic profile is represented. The upper layer is a sand with thickness of about 2 meters and a permeability of 5 times 10 to minus 5 meters per second. The second layer is a clay silt with a permeability of 10 to minus 8 meters per second. Then there is a silty sand and finally a sand with gravel. Close to the old embankment on the Po River, an experimental embankment was built in order to obtain a pool that was possible to fill and, by this way, to simulate a flood. The experimental embankment can be divided in two different branches, each one built with a different kind of soil. The soil type A is a plastic and compressible fine-grained soil, while the soil type B is less plastic and compressible. For each branch, a section was instrumented with tensiometers and piezometers. However, laboratory suction control tests were carried out only on soil A. For this reason, only the section A was modeled. The properties of the soil A post-compaction are shown. Also temperature, rainfall, air relative humidity, velocity and direction of the wind were monitored. These are necessary to calculate correctly the evapotranspiration. The potential evaporation has been calculated with the Penman-Montet equation, while the actual evaporation has been calculated multiplying by the potential by a drop coefficient. Both are calculated according to FAO guidelines. Results from the monitoring and the flood simulated are shown in the slide. As can be seen, two different historical floods were simulated, a long flood with a low peak value and a short flood with a higher peak value. The software CodeBright was chosen to analyze the problem. It is a FEM code that allows to perform coupled thermohydromechanical analysis in geological media, developed at Universidad Politecnica de Catalunya. It is implemented in JIT that performs the pre-processing and post-processing. During the period at UFPA, two kinds of analysis were performed, hydraulic analysis and thermohydraulic analysis. When an hydraulic analysis is performed, the liquid pressure is unknown and the mass balance of water is solved. The temperature and the gas pressure are kept constant. In the thermohydraulic analysis, instead, the temperature is unknown and the balance of energy is solved. The vapor can be allowed or not. Using the thermohydraulic analysis, it's possible to consider the coupling effect, but it also allows to use the modulus atmospheric of CodeBright. Irrespective of the kind of analysis that has to be performed, the geometry is the same. As can be seen, the model has been simplified in order to have faster analysis. The other detail that has to be explained is the fact that two columns at the sides of the geometry and the pool have been modeled. The reason is that the software doesn't allow to apply a piezometric head on the boundary, but only the liquid pressure, so in order to apply a water level at the sides of the model, it was necessary to create the two permeable columns. For the same reason, it was also necessary to model the water in order to model the flood. Hydraulic properties to the materials and hydraulic boundary conditions have to be assigned. The lower boundary from node 23 to 24 is impervious, the same for the left and the right ones. At the base of the permeable columns, the water level in the Po River and in a piezometer have been used. On the field, a seepage surface that allows only outflow is used. The analyses have been performed with and without considering evaporation. In the analysis with evaporation, on the surface of the embankment is applied a flux variable with time, that is the net balance between the daily evaporation and rainfall. During the simulation of the flood, on the wet surface is not applied any boundary condition because the water is activated and the line 6-8 becomes a part of the domain. In order to do the analysis, the soil water retention curve and the relative permeability curve have to be assigned to the materials. For the soil A, parameters obtained from the curve fitting of laboratory tests have been used. The intrinsic permeability, measured in laboratory tests at different porosities, has been chosen as an average value in the range of stresses expected in the embankment. The program requires also a function for the intrinsic permeability that changes with porosity, even if porosity is constant in the model because no displacement is calculated. Because of the fact that also the water and the permeable columns have been modeled as materials, also the hydraulic properties for them has to be assigned. The desired saltwater retention curve should have a very low entry value. And after that, the curve should be very steep, like the relative permeability curve. The problem is that a curve with these characteristics causes convergence problems. In order to obtain a steeper curve for the relative permeability, other two functions have been tried, the generalized power and the power with initial cutoff. The second one is very interesting. Thanks to the cutoff, the permeability with degree of saturation lower than a value is 0, so it will be perfect for the water. Ideally, the cutoff should be 0.99. The problem is that when the cutoff is too high, the water cannot fill the pond because the pond becomes impervious. After many tests, the function with a cutoff equal to 0.1 was chosen. This is a video of the hydraulic analysis without evaporation. Only positive liquid pressure have been showed. As can be seen, the first flood that has a very long duration begins to saturate the embankment only after 15 days. The second historical flood that has an exceptional high water level instead doesn't seem to saturate the embankment. This can be seen better in this comparison made between the liquid pressures in the embankment in the first flood and those in the second flood. As can be seen, the first flood, that is longer but with a lower pitch, saturates the embankment more than the second one. Another comparison has been done between the analysis with and without evaporation. In the lower picture, in the white portion of the embankment, the suction is higher than 0.08 megapascal, so the suctions are higher, and the whole distribution of the liquid pressures changes in the embankment. The second step of the work was to learn to use the thermohydraulic analysis. In fact, by this way, a coupled analysis is performed. This allows to consider the vapor and the effects of temperature on hydraulic properties like viscosity and density. The most important advantage is that it allows to use the atmospheric boundary condition, that is the modulus of Rodbright made for the atmospheric conditions. In order to make the thermohydraulic analysis, the temperature has to be assigned on the boundaries. Under the filled surface, the temperature has been imposed to 15 degrees. On the filled surface instead, the atmospheric temperature measured inside has been applied. It has to be noted that at first the evaporation was applied as a flux, so the atmospheric modulus of Rodbright was not used. It is also necessary to give thermal properties to the materials. These properties depend on the degree of saturation. The curves have been chosen from literature. This is a comparison between the results obtained with the hydraulic analysis and those obtained with the thermohydraulic analysis. It has to be noted that the gas pressure is 0.1 megapascal, so the absolute pressure is showed. It can be seen that the influence of the temperature on the hydraulic properties is negligible. So, more interesting is the atmospheric modulus that allows to apply directly the meteorological variables. The evaporation cannot be applied but is calculated from the software. For this reason, some parameters have to be assigned to the program. Moreover, the software can calculate the radiation if wanted based on the location. It is also possible to multiply the rainfall and evaporation by a coefficient. In order to calculate the evaporation, the atmospheric temperature, gas pressure, relative humidity, cloud index, radiation and wind velocity have to be assigned with time. They can also be simulated by the software, but in our case, temperature, humidity and wind velocity have been measured. Atmospheric gas pressure can be regarded as a constant, while cloud index and radiation have not been measured. However, the radiation has been calculated based on the FAO guidelines. with a method that accounts for the cloudiness of the sky, so the radiation has been imposed like the calculated one, while the cloud index has been set as 1. The sections estimated with atmospheric boundary conditions are higher than the previous one. In fact, in the second picture, in the white portion of the embankment, the absolute liquid pressure is lower than 0.4 megapascal. So, in conclusion, the software CodeBright was used to analyze the experimental study performed in Viadana. Hydraulic and thermohydraulic analysis were performed. The thermohydraulic analysis were performed also with the atmospheric modulus of CodeBright. The effect of evaporation is not negligible and allows to estimate suctions that in the embankment that are closer to the measured values. The effect of temperature on the hydraulic properties, like viscosity and density, seems to be negligible. The atmospheric modulus of CodeBright instead will be further investigated, in particular the way to calculate the evaporation, because it is the more proper way to calculate it.